The figure shows the chain drive of a bicycle. How far would the bicycle move if the pedals are rotated through 180 degrees? Assume the radius of the bicycle wheel is 13.6 inches. Okay, so the purpose of this problem is to illustrate applications of radian measure. And so with radian measure, it's simpler to calculate arc lengths of circles. And so a problem like this involves arc lengths. So radians would potentially be useful to use here. That's what we're going to do. So, okay, so this piece is attached to the bicycle wheel. So the idea is if we can figure out how much the angle that this rotates, if this drive spoke or gear, I'm not sure what they call them on bicycles, this drive wheel here, if when that rotates 180 degrees, what angle does this rotate? And then with that, we can figure out how far the bicycle moves. So, okay, but we need to figure out how much does this rotate. If you've pedaled and you rotated this 180 degrees. So the key to solving problems like this is, with meshed gears, or here, these are meshed with a chain. So any kind of gear like this has what's called like a pitch circle or a pitch diameter. And all that's representing it's the diameter that like of where like the chain is gripping, right? You can't think about the diameter, the outer diameter of the gear as going all the way to the edge of the teeth. It's more like the pitch circle. The pitch diameter is the diameter location where the teeth are gripping. And so the idea is the key to solving problems like this is that the pitch diameters of these two gears are like married together. If the pitch diameter of this moves, then the pitch diameter here has to move at the exact same time. And so what that means is that any distance that not the gear rotates, but the pitch diameter, any distance that this pitch diameter rotates, this is going to have to rotate the exact same distance. That's the key to solving problems like this with meshed gears. Either they're meshed like physically in contact or they're meshed with a chain or belt. So, okay. So let's figure out how much like circumference this has rotated through after 180 degrees. And what do I mean by circumference? Well, what arc length, right? How much arc length has been kind of mapped out by the 180 degree angle over this circle here. They're representing this as like the pitch diameter. That's going to be the exact same as here. Okay, so if we convert to radians, because radians is really simple for arc lengths, right? So 180 degrees in radians is, well, we know that's pi. Okay, so the arc length that mapped out here is just pi times the radius. See, really simple when it comes to radians. Inches. Let's just leave the pi for now. Okay, so there we go. So now we know that since when this rotated 180 degrees, that means the diameter of this circle, the circumference, rotated this length. So what does that correspond to in radians then? That's why in order for this circle to go that same distance, it's going to rotate faster. This is going to be rotating slower than this because it needs to go the same distance, but it's a smaller diameter. So, okay. That's why when you look at like gear trains, the smaller gears are rotating faster than the larger gears if they're like meshed. So, all right. S is equal to R theta. So theta is equal to S over R. So we've got 4.72 pi divided by 1.38. And let's go ahead and just get rid of that pi. So 4.72 times pi, we'll let that get absorbed into the calculation. So 10.75 radians. Okay, that's what this gear has rotated. And you might think, well, that's not a lot, 10.75 radians. This isn't degrees. This is radians. 2 pi radians is like 6 something, so this is more than a full revolution. This went like a half revolution. This went more than a full revolution. Okay? So now, how does that translate to how far the bicycle moved? Well, this gear is fixed to the wheel. They're fixed, like welded together. So what that means is that if this rotated 10.75 radians, then so did the wheel. Okay? So here's the wheel. If it rotated, so something like that, that's around 10.75 radians. There's theta. Well, okay, well, how does that translate to how far the bicycle moved? Well, what you can think about to figure that out, think about laying out that the circumference of the wheel over that entire rotation, right? Because like each point had to like touch the ground. Each point of the circumference had to touch the ground over its entire motion, right? Each point of the circumference. So it's really, you're thinking about the linear motion is the same thing as the amount of circumference that kind of touched the ground as it went along. So what does that translate to, this theta, as far as arc length of the wheel? Well, the wheel is 13.6 inches in radius, so r theta, 13.6 inches. Theta is dimensionless. So they're 10.75 times 13.6, so 146 inches. You can convert that to feet, a little more intuitive, about 12 feet.